So what I have here, this is a picture of Sir Adam Beck Power Station. If anyone's seen this, if you're going down to Niagara Falls will be way down here. You drive along and then you can actually, you're driving on top of the structure. You might not even realize it, that you're on top of this gigantic, it's like not quite a dam, but it's still quite large structure here. Okay, it's equivalent to a dam. It's not like Hoover Dam, but still quite large. So what you have here, you got these generating stations. This original generating station on this side, I think it was built in the 1920s. So this is in the 20s, and this was built in the 50s. That's why there's a difference in design. We have Sir Adam Beck 1, Sir Adam Beck number 2. And I think between them, they've got 26 power stations or generators, so 26 generators. And I think they produce around 2,000 megawatts of power. That's their rated capacity. So to give you an idea, the world's biggest power station would be the Three Gorges in China. I think that's about 10 times larger. Okay, so this is a big power station, but by no means is it the largest. Okay, and the reason is simply we only have so much water in this river. It's the Niagara River, and it's not one of the larger rivers that we have around here. And the height difference, it's big, but it's not as big as some other locations in the world. So we take advantage. So what's happening in here? Let's look at the power or the energy changes. Do you guys remember energy transformations way back when, right? So let's talk about them. So at the top, we're going to have our water. We're going to have our gravitational energy, and it's going to fall. So it's going to be falling. And then at the bottom, the water is going to hit one of these turbines. That's what a turbine looks like. That's one of the newer turbines that they're upgrading some of the generators with over here. So you have this turbine over here. So you can have a turbine spinning. So you have another EK over here. And then you have this thing. This is a little generator, and there's a guy in here. Just to give you an idea, this is how big he is. That's the size of the person. So these are massive, massive, massive generators. And the idea is we're making electricity at the end. So I want you to remember this. In order to get electrical energy, you have to get that energy from somewhere. Where is it coming from? So here it would be from EG, so gravitational potential energy. Other stations, again, we have fossil, we have got natural gas stations. We also have basically stations that have nuclear power, fission powered stations as well. They're the ones that form the majority of energy, electrical energy in the province. But it's important to understand what's going on, the whole idea behind this generator. I'm going to show you a very quick clip here. It's actually a really, really cool clip I found on the Hoover Dam. Now, I was trying to find one on Sir Adam Beck, but they didn't have really good ones, unfortunately. So I'm just going to show you. Where is it here? I think it might be here. One of the tabs I have here. Where is it? Uh-oh, I think I might have lost it. Uh-oh, it's not good. Hold on. Not a big deal. I'm just going to go to the website, our handy dandy website. Don't forget to refresh. And this is what we're doing today. So by the way, one thing I'm going to do is this. I was going to do all these applications. I'm going to put down, you don't have to worry about them. Okay. We're going to ignore those. We're going to be focusing on just something called magnetic induction. So here's the Hoover Dam one. I'm just going to show you very quickly. Yeah, we'll go through the quick ad.
20 million people use Grammarly every day to improve their writing.
There we go.
There's the generator.
It doesn't really vibrate.
Going down by the generators, the giant generators. Check this out. There's Lincoln. Lincoln, look how big that is compared to you. There's the generator.
It doesn't really vibrate that much, which is kind of surprising.
That is surprising. There's a lot of power going through that right now.
That's the one that powers all the dam.
What's inside a giant generator that generates power and electricity for this entire dam structure? We just happen to be here when they're taking apart one of them. So you have these giant buckets that the water's going to push and spin this around, which in turn, those are all magnets that go all around. This is it. You're seeing it.
There you go. So I think it's really, really cool for you guys to see that. Now, you notice the bucket design is very different. The turbine design is very different than the one I showed you here. So those are the old-fashioned ones. That's what we had in here as well. Now they're being upgraded to make them much, much more efficient. You want to get every bit of energy you possibly can from the water in order to go on. So how do we make power? Well, I'm going to show you something. So what we have here, I'm going to show you is we're going to review a couple things first of all. Now remember, way back when, what we did, I'm going to shut the camera off just for a second. I have to move it here, so we're not going to get all seasick. Give me a second. All right, let's see how this is going to go. I'm going to try to turn the camera app on just so I can kind of control it a little bit better. There we go. So what we have here, let me just go over here. This is what we have. We have my power pack here. And the power pack, what I'm going to do is I'm going to use the power pack, run current through this coil. We've done this before, right? So here's my coil. You can see here, the positive charges are this way. So they're going up. Hey, where would the north be, do you guys think? Is the north, let's review our right-hand row. It's actually perfect time for that. Where is the north going to be? Is it going to be on the right side or the left side? What do you guys say? Right or left? Holy smokes. You guys are, I just turned my head and I already have like a million answers. You guys are good. Yeah, left side. So here we go. So there's my current, flows like this. There's my thumb. This should be the North Pole. Let's see. We're going to make sure that's the case. How do I do that? I'm going to use my compass here, my little compass. So my compass right now should be pointing, if this is north, should be pointing out. All right. So let me move this over here. Bring this lower. All right, here we go. And let's see what's going to happen with my compass. Turn that on. Oh yeah, take a look at that. I shut that off. It goes back to normal, okay? So what I was able to do is, I remember, this is amazing way back when, we're able to make magnetism from electricity. So electricity to magnetism. They're related though. So what if I wanted to do the opposite? What if I want to use magnets to make an electric current? So I need to have some kind of way to do that. So the way I do that is this. Let me see if we can show you how this works. All right. Okay, here we go. All right, so what I have here, nothing crazy. This over here, there we go. What I have here is I've got a bunch of coils and they're hooked up to a current meter. This is like an ammeter. Remember, you guys might have used ammeters, but this one can go positive and negative. So when you have a positive negative ammeter, we have a fancy name for it. It's called a galvanometer. So here, it's going to detect my current flow. So I'm going to have here a magnet. See, I got strong magnets here. So I'm going to use this magnet to produce some electric current. Let's try that. So I've got this magnet, and what I'm going to do is I'm going to bring it towards this, like this. Here we go. And you know what happened, I think? Hold on. Oh, here we go. If you look at the needle, no, it's not working very well. I think we have a loose connection here. Hold on. Let me see if I can fix it. This connection's torn in the past, so it might not work the way I want it to. It was working perfectly, but I think when I moved it today, it stopped working. Oh no. Let me see if I can make something work here. Let me see if I can take this one. I'm going to try to take this coil here we had before. And this might work, may or may not work. I haven't done this before, but there's a break in the wire here, and that's why this isn't quite working the way I want it to. We'll give it a shot. If not, we'll show you in the simulation how this would work. But I like to use real equipment if possible. I think when I was moving this from school, I scratched the back of this, and there's some paint on there, it's conductive paint. So let's see what happens here. So I'm going to do the same thing. Let's see if we can get this dial to move. Oh yeah, check that out. There we go. So you can see here, I'm going to bring this in. The current goes one way. I bring this out, the current goes the other way. This is actually working way better. Okay, so the idea is I can use a magnet to produce electricity, but here's the problem though. The second I put the magnet in, yeah, we've got current flow, but look what happens when I leave the magnet inside. The current flow stops. I take it out, it goes the other way. So it's only when the magnet is moving or when the coil is moving in relation to the magnet that we have the current flow. So we need to have this. We need to have a changing magnetic field. So as this magnetic field gets closer, sorry, let me bring this over. As this magnetic field comes here, it's going to get stronger and stronger. It's changing. And then when I take it away, it gets weaker and weaker. So it's only true if you've got a changing magnetic field. So what we did is the basics of a generator. Now, if you have a real generator, let me just move this out of the way for a little bit. So a real generator would look like this. And this is the one we have from school. Unfortunately, this is the one that's broken. All right, it's the broken one. So we have two of these. The other one, I think someone was using, so I could only have this one. But what a generator is, it's very, very similar. So here in a generator, you've got this. You have coil here. There's my coil, and it's going towards and then away from these magnets. So I've got these two magnets. So it's almost the same thing. So what's going on here, let me just show you, would be this. Let me just zoom out a little bit. So what's going on is this. It's almost like this. I have a magnet here, and then this thing is going turning. See, it's going towards and then away from this. So it's like this little coil spinning. And that's what's going on here. So this would be my magnetic field, and this coil is spinning around. And we'll be looking at how this works in a little bit. Now, you don't get energy for free. So remember, what you have to do is this. You need to put energy in. So I have to push with a crank here, and my energy here gets changed into electrical energy. So remember, energy is not free. That is the key thing. So I'm going to show you the simplest motor. The simplest motor I can think of. It's this thing here. Now I just have to find, I forget where I put my magnets. Here they are. So what I have here, I've got a piece of copper pipe. Now I don't know how cool this is going to look. I'm not sure. What I have here is a piece of copper pipe. I'm going to zoom out just a little bit on this side so you can see probably better on this side with the white wall. And I can go back a little bit. There we go. There's my beautiful wall there. So what I have here is this. I've got a piece of copper pipe. You can see that it's hollow. There's nothing fancy about this. Completely hollow. So what I'm going to do is I'm going to drop this thing. This is just a piece of metal. So if I drop the metal through here, here we go. Drop the metal. At the top, I'm going to drop the metal. Here you go. Oh, okay. I'm letting go right now. It falls through. No big deal. So again, I'm going to show you. There's my metal. You can see it there. I'm going to drop it. Oh, and it goes right through. Nothing happened there. Here, I've got a strong magnet. I'm going to do the same thing with the magnet. Let's see what happens. Put the magnet in here. And what the heck is going on? It took forever for this to fall through. So let me show you a view from the top. Let me see. I don't know if it's going to work. Let me see if I can get it going like this. It may or may not work. Let's give this thing a try. Oh, there we go. Let me see if I can hold it nicely for you guys. So here we go. Okay, and let me just line it up nicely. It's hard. There we go. Okay, so let's see what happens here. It's falling, but it takes a really long time to fall. And eventually it's going to come out at the bottom. Oh, there it goes. So it's a very slow fall. Very slow fall. So I'll show you another, it's the same thing. Here's another copper pipe just to show you, again, how this works. And we'll talk about how this leads to current flow. So here's a longer pipe, much longer pipe. Same idea. I'm going to drop this from the top. Here I go. I'm going to drop the magnet. Oh, I thought it was stuck. It took so long to get out, right? So really cool. So you have a strong magnet. You can just pop it into any kind of copper pipe and goes through. But here's the thing. Why did it do that? Why it slowed down? It really slowed down. So there has to be some kind of force here. So as this is moving through here, there has to be some kind of force going against the force of gravity, right? So if I draw a little free body diagram, I'm going to have a force downwards, force of gravity, and there's another force going upwards, and that's the magnetic force. It's actually, as you're going down here, this makes a magnetic field in the copper, and this magnetic field pushes this back up here. So the idea is, as you're falling, you're making another magnetic field. We'll talk about this. So this is a cool application. We have a really neat application at Wonderland. One of the rides is based on this. Okay, you guys might have even been on it before. So I'm just going to put this over here, out of the way. Give me a moment here. Sorry. We'll just put it right on top there. There you go, beautiful. Okay, so it's gonna shut the camera off for a second. We're gonna go back to our regular lesson. Just be a moment. Okay. All right, so I'm just gonna leave the camera off just for a bit. So what I'm gonna do is I'm gonna go through a note that you guys have. So go to workbook 144, 144, 144. Find 144. Okay. 144. We're gonna be looking at the left side. We're gonna do it in sequence. So it's going to move some stuff out of the way here at my end. So 144, that's where you should be. Okay, so 144. So what we saw was initially when I showed you the coil, I used electricity to make magnetic field, right? So we did this. We had electrical energy. And it's really the same thing. Let me just change the thickness here. It is really the same thing. There's not much of a difference here. Here we go. So we're going to have electrical energy changed into magnetic field. Okay, magnetic energy. And basically what we do, we have a current flow here. So the current flow is going to go like this. You get the current flow. And the current flow is going to be making a magnetic field. All right. And we already know the direction of the magnetic field using our first right-hand rule. Here's my magnetic field. I should have used opposite colors. Oh, let me just change them around here just to be consistent. There we go. And I make this over here green. Yeah, just to be a little bit more consistent. There we go. So basically the charges here, as they move, they make this magnetic field. All right, so nothing fancy. This is just regular solenoid, okay? So this is a solenoid, nothing crazy. Then here's what we did. Michael Faraday, remember he's a big guy in electromagnetism. Remember he figured out the motor principle. He also figured out something called magnetic induction, magnetic induction. What he showed was you have a magnetic field, but it has to be a changing magnetic field. And the changing magnetic field is going to make an induced current. Induced current. So over here we should have induced electric current. So what happens is this. When your magnetic field is changing, it's going towards or away from this coil, or vice versa. So basically the two are moving in relation to each other. They could be moving either way. And what happens is this over here could be either a north or a south pole, depending on which way this is moving. We'll talk about the rules in just a little bit. And that's going to make current that goes one way. Oops. Should be right here. That current that goes one way, like this, or goes the other way. It can go back and forth, just like I showed you in the coil here. The current can go one way or it can go another way. So the charges go back and forth, right? So this is called my induced current. So this is my induced current. And it reverses. It depends on the magnetic field. Now, when I bring this magnetic field close to this, it's going to make another magnetic field. So this magnetic field can go either way as well, depending on which way this is moving. So this is going to be called my induced magnetic field. So this is my original magnet. And then as you're bringing it closer or further away from this coil, the current goes one way or another, and the magnetic field goes one way or another. So this is the whole idea. A changing magnetic field induces current flow. This is Faraday's principle of induction. So we're making current flow. So these charges that are moving, when they're moving, they make their own magnetic field. They go one way, they make a certain magnetic field. They go the other way, they make the opposite magnetic field. So that's kind of what he did. It's a really, really, really neat thing. So he basically played around with this, and he's the first one to be able to show this really, really cool phenomenon. Let me just show you a very quick clip based on that. Here we go. Okay, it's a Veritasium. I love this channel. It's a really good channel, so I highly recommend it if you're into YouTube. So this is what they did. They go through, and you know the demo that I showed you with that pipe? They're showing the same thing to people. And then they get into Faraday.
Does it like...
It kind of tilts.
I think it's the powers of the universe.
I don't know why it's doing it.
Well, this is what's exciting, is only a few blocks from here was the lab of a guy called Faraday.
In October 1831, he built the world's first electric generator here, a magnet which you push and pull in and out of a coil to generate electric current.
So that's the actual...
Yeah, world's first electric generator.
And there's a permanent magnet in the middle?
There's a permanent magnet, yeah.
It was Faraday who realized that it's a changing magnetic field that actually can generate electric current. So as the magnet is falling through the pipe, it's creating a changing magnetic field that generates little electric currents, so-called eddy currents in the pipe, and they create an opposing magnetic force on the magnet, slowing it down.
Okay, and we'll get back to that in just a little bit. Okay, so we'll get back to that in just a little bit. We'll talk about applications. So cool stuff, right? Yeah, I know. Nice channel. So what I'm going to do is I'm going to go through a brief overview of this particular part of the note. You're going to see that I've got more detail here. Okay, there's way more detail here, and you guys can do the more detailed note later. So just listen for now. I want you guys to understand, and then later you can copy down this information. Okay, so listen right now. So what happened was this. Heinrich Lenz, he figured out what's happening. He added the next piece of the puzzle. He figured out that whatever you do, the magnetic fields oppose each other. So let me show you what happens here. So let's say we've got a magnet, and you move a magnet towards a coil, or the coil is being moved towards the magnet, but you're going towards. They're going towards each other. So what happens is this. So if I push this way, this is a north pole, right? Well, it's going to fight me. It's not going to have self, because if I had a south pole here, what would happen? This would go in automatically and it'll be attracted. I wouldn't have anything to do. So what we have here is the following. We got a simple coil. Remember, there's nothing hooked up to it. It's just a bunch of wires, nothing else. There's no battery, anything like that. So what happens is as you're moving towards this, you're going to have an induced pole here. Now, this induced magnetic field is going to oppose you. Just remember the word oppose. So if I'm going towards this, it's going to oppose me. So that means it has to be repulsion. This is going to be a north, right? And then this would be the south. So if you look at the magnetic field around here, it would look like this. Let me just show you some magnetic fields. So this would be the magnetic fields. So the magnetic field here would be like this like that, right? And you also have this magnetic field. And this magnetic field, again, is the same way. So they're going to be repelling. This is kind of what you're doing behind the scenes. So this over here, this is in the coil. This new magnetic field that I'm making is called the induced magnetic field. And it's only there when we're changing the magnetic field. If I stop moving this magnet here, this disappears. Boom, it's gone. So this is going to be there. Now, the reason we have this is because we have current flow. So as I'm bringing this magnet towards the coil, it's forcing the charges in here to move. So how would the charges move? Well, according to the right-hand rule. So they would be going downwards here. This would be the induced current. So this is the induced current flow. So when I'm going towards this, the current flow is going to be going like this. And this is called my induced current. So what happens is this changing magnetic field, and we called it the external magnetic field. So changing, it has to be a changing external magnetic field. What it does, it induces these charges to move. The charges move, and when they move, they create a field here, the induced magnetic field, that opposes the original external magnetic field. They oppose each other. They fight each other. So let's look at what happens if I move this same thing away. Now, this time when you do this, it's also, this magnetic field is also going to oppose you. So if I'm going away, so if I'm going away, it's going to fight me. It won't let me do that. It's like fighting. It's force. So the reason for that is because we're inducing a south pole now. Now there's attraction. So it's fighting me. If I want to pull towards, it pushes away. If I want to go away, it tries to pull me back in. So it's always opposing your motion. That's the key thing, opposing your motion. It's fighting you. That's why I have to put energy into these generators. So what happens is this: if this is going the opposite in terms of the magnetic field, the current flow is the opposite way. So the charges now move the other way. So this would be the new induced current. And then you're also going to have the magnetic fields here. So this would be your two magnetic. So here's my magnetic field. Here we go. And this time the magnetic field is opposite what we had before, opposite. So the whole idea, whatever you do, it won't let you do that, okay? It's going to fight you. It's going to fight your motion. So what I'd like you to do is, can you tell me which pole is going to be here on these ones here? So what pole is going to be here? What pole is going to be here? And remember, whatever you do, it's going to fight you. So up here and down here, what are the poles going to be? So I want you to think about that just for a second and let some people in here. All right, so let's take a look at this. So what we have here is we've got, remember, I'm going towards this. It's going to fight me. If it's going to fight me, what we're going to do is we're going to have the same pole. It's going to be repelling me. It's going to be pushing back. And here, if I'm moving away, it's going to attract me. It's going to be opposing me. So this has to be a north pole. So again, whatever you do, it's going to resist you. So if I'm going towards it, it's fighting me. I go away, it's fighting me again. And the whole idea here is you've got this current flow, So here the current flow would be in this direction. Okay. And then if I'm doing the opposite thing, the current flow is going to be in the opposite direction. So you can see here, doing opposite things will make the field go opposite ways. So when you look at the note that you're going to be copying later on, this is what it looks like. Okay. So the whole idea is that you've got this induced current, the red, that makes a magnetic field that opposes your motion. Whatever you do, it's going to fight you. It's going to resist your motion. And that's the basis of most generators. So let's take a look at this. Here we go. I'm going to go back to that in a little bit. So this would be a generator, okay? So remember we said we have a generator is basically something that's spinning around. This is just the other side of the page. And this is something you could copy, but let me just clear this first. So what we have here, I've got this generator, and the generator, let me zoom out just a little bit. You can see here how the generator is spinning. It's spinning, right? So it's going clockwise. So it's doing this clockwise rotation. Sorry, I just lost my stylus here. So it's rotating in this direction. So it's going to be rotating clockwise. See, it's rotating clockwise, up like this, all right? And what we're going to do is we'll be looking at little snapshots of this red section, okay? And we're going to focus on this side here. So this is what a generator is. So basically a generator consists of this coil and it's rotating inside an external magnetic field. So this would be my external magnetic field. This is something you can label. Okay, external magnetic field. I'm going to zoom in a little bit. There we go. So what's going to happen is this. We are going to have this over here. We're going to focus on this. This is going to, when we're moving away from this. So you're going away from this side here, away from north, and you're going towards south. So what's happening, if I'm going away from this, it's going to fight me. It's going to resist me, and we're going to have the attraction here. It's going to attract on this side. So this should be a south. That's going to be a south. And here's the other thing. This is going to be moving towards this. So it's also going to repel me. So this is going to be, is repelling on this side. So you have attraction here, repulsion here. So if I'm going towards this, it's going to fight me. It's going to be repulsion. So this has to be south. So again, south. So again, towards the south, away from north, this is opposing my motion. So here we've got repulsion. Here we've got attraction. It's fighting me. And then what happens over here is I'm still going towards the south. So still towards the south. So you're still going towards this. It doesn't want to let me do that. It's still going to oppose my motion. So it's going to be south. And then what happens is over here, we're right in the middle. There's nothing there. I can put an X there. Nothing happens. There's no current for a second. And then as I'm going away, now look what happens. I'm going away from south. So it's going to fight me. It's not going to let me do that. So this is going to become a north. And again, this north is going towards this. So it's also going to have repulsion here. So basically it's fighting me here. It's fighting me on this side. Here it's attraction. Here it's repulsion. It won't let me do what I want to do. And you can see here that we're going towards the north. So repelling away from the south. Here it's going to be attraction. So let me just add these in over here. So repel towards north. Attract on this side, away from south. So again, whatever you do, it opposes you. So that's kind of the idea here. So let's go over here and look at what happens in terms of the other pole. I'm going to go back up. So here, if this is south, this is going to be north. This is going to be north here. North on this side. And then we continue our rotation. North. Oh yeah, we forgot to put where the south is here. South. And then we're back to normal. We have X's here. Whenever we're like this, there's nothing happening. Whenever we're parallel to the external magnetic field. So based on this now, I can use my right-hand rule. So I want you guys to figure out which way the charges are moving here. Which way are the charges moving? I want you to put them in there. So use your right-hand rule for solenoids. Which way would the charges be moving? I'll turn my camera on. I'm going to show you in just a little bit. All right, so here we go. So what's happening here, remember, this is going towards this. It's going to fight me. It's like, won't let me go this way. So it's going to repel. And it's also repelling on this side because this is going towards the south. So you've got repulsion. And here, we're going to have attraction because I'm trying to go away from the south. So it's fighting me. Whatever it is, it's fighting me. So this is north, that's south. Which way is the current flow? There's my thumb. Which way is the current flow? The current flow is like this. Okay, so on here, let me just show you the current flow. It would be upwards here. Upwards. Okay, and oh, I think I missed this one too. I missed this one at the top, sorry. So here would be the same thing. This would be my current flow here. This is a bit awkward for me to do, but I can still do it. Ah, there you go. My hand's at the side. But you see how the current flows like that. Now, down here, so if I follow this, my current flow would be negative, positive. Right? So this would be negative, positive. Now, at this point, when we're perpendicular, there's no current flow. So no current flow. I'm just going to put an X there. Now, what happens here is my, oh, I made a mistake here. This should be south. Let me just fix that. This should be south. So now what happens is this. When I'm rotating this way now, so I'm going away from the north, it's going to fight me. This is going to be a south pole. Remember, it's whatever you're doing, it wants to do the opposite. So it's going to fight me. It's going to attract. And as I'm going towards the south, it's going to repel here. So it's fighting me. So it's going to be a south pole. And then if I figure out the current flow, I'd use my right-hand rule. So there's my north. And what's happening? Here we go. Ah, that's kind of awkward, but I can do it. So there's my north. Current flow is down. So this will be my current flow here. Let me just select a color. This would be down, right? And negative now is on this side. And the same thing's true here. Current flows like this. Oh, wait, sorry. To fix it here. Made a boo-boo. Okay. And I guess this is tricky. I get it. Just remember this. Your current flow depends on the North Pole. So what I do is I look at where's the north and the south going to be based on what's happening. And then once from that, I figure out the current flow. So you can see here my current flow. Look at this side. The red side right now is negative. What was it before? Before the red side was positive. So you might want to highlight that one end that I have there. So as we're going along, what's happening is the current, look at this, positive. And then later, the current is going to be negative. Negative here. So it switches over and it keeps switching back and forth. So that's why the needle goes back and forth like that. All right. And that's what you'd see on the generator, where the needle will be going back and forth, back and forth, back and forth. So this is just a fancy example of induction. Okay. So I have this also posted online, right? If you missed something, but the idea, it's the exact same concept as we had before. So this is the same. Okay. It's exactly the same as this. The only difference here is that this coil is spinning. That's the only difference that we have. Let me just shut the camera off just for a second. Shut the camera off, not the mute. Okay, so let me just show you again on the generator here. Unfortunately, again, the generator doesn't work. It's too bad, but that's okay. Let me just show you here what would be happening here. Yeah, just give me a moment. Just want to get this camera stabilized somehow so it's not wiggling everywhere. And get the camera up happening. There we go. So right now, so if I've got this would be my coil. Right now, there's no charges. There'll be no charges in here. Let's get my fancy pointy device. No charges anywhere here. Now, the second this is going away, let me put this on top. You guys can see. So if this is moving now like this, if this is moving like this is going right now, this coil is going away from the south towards the north. So it's going towards the north. What pole do I have here right now, guys? What pole would this be? Remember, it's going away from the south towards the north. What pole would this be? Remember, we're fighting here. It's resisting my motion. So again, here I go away from the south. It's fighting me, won't let me. So it's going to be north here. And then going towards north, it's also going to fight me. So right now, this would be a north here. And then I would go the other way. So right now, still north. Now it's going to be 0. Now look what happens. I'm going away from the north towards the south. It's going to switch over to a south pole. And that's kind of what I'm trying to show you here. And this is going to rotating round and round. It's switching the current. And here's an animation. I'm going to show you a very quick animation. I know it's tricky. You have to practice this a little bit. Here's a little animation for you guys. Like a little simulation. Let me see if I can find it for you guys here. Here we go. Bring this over here. Okay, you can see what happens here. Right, so we're going towards this. Current's going one way. It's going down. Now the current's going up. Now it's going down. Now it's going up. And this is what's happening. So again, this is what's going on behind the scenes. So I'm going to just stop at one point here. So right now, we're going towards this. Let me just turn the camera on for a little bit. Okay. So we're going, this is going towards the coil. This is going towards the coil. So if I'm going towards the coil, it's going to fight me. So it's going to resist my motion. So this is going to be a south pole. This is going to be my north pole. So the current flow should be in this direction, upwards. Let's see if that's the actual case. Oh, wait, hold on here. Let me just think about that. Wait a second. So it's going, yeah, it's going down. So it'll be, oh yeah, sorry. That's right. I was right. So there's my south, it's induced south pole. There's the north. So the current flow, we're looking at the current flow in the front where my fingers are. The current flow is going to be going down right now. So this is north, south. So we're inducing a south pole here because of the current flow. So the current flow is downwards. Here we go. Okay, so downwards. And now what happens is this is going away. So this is going to fight me. So if it's going away, this is going to be a north pole. If this side's the north, now the current should be going upwards on the front. You can use your right-hand rule there. And there you go. And then it flip-flops back and forth. And that's how you get AC current. That's what we use in Canada. We use AC current because it's very easy to produce electricity that way through these generators. So on your page, we'll talk about that in a little bit, okay? So just remember, for diagrams like this, just think this end is going away, so it's going to fight me. So it's going to be a south pole, okay? And it's going towards this, so it's also going to repel on this side. So it's going to repel on this side. So again, south. So you have repulsion and attraction on this side. Oops, let me just go like this. So it's one of those things you have to play around with that. It's just kind of quirky at the beginning, but then once you figure it out, it's very, very easy. So play around a little bit. This is trying to show you the same thing on this side. Don't worry about all the parts. It's all you have to know is just this, okay? So if I give you a diagram, I would expect you to be able to label this. Or if I gave you one of these, it's the exact same thing. One of these, and you should be able to tell me where the north is and which way the current flow is for these. Yeah, that's it. So that's all you have to know for today's lesson. But it's important just because this is how we get our electricity. It's important to understand magnetic induction. So again, this magnetic induction. So let me talk about this now. What happened with that magnet inside the coil? That's what you have at the bottom. So what's going on here is this. The magnet has a north side and a south side. So if it's going down this way, this magnet going through here, it actually makes a circular current in here. The current is circular. And here's how you figure out which way the current is going to go. Let me just fix this a little bit here. So the current is circular down here. I'm going to use a different color too. Let's use blue for the current. Okay, there's my induced current. And just listen for this part. You guys will be able to copy this page later. Now, the direction of the current could be one way or another way, right? How do we know which way it is? Well, the way you know is this. If this is south, this is going down. Remember, this is going to fight me. It's going to repel. What pole do we have to have over here, guys? If we're repelling, what pole do we have to have right here? What pole? Yeah, south pole, right? So you're making an induced magnetic field. It's fighting me. Remember, it's fighting me here. So if the current flow here, if this is south, this is going to be north. And then if I use my right-hand rule, let me switch to the camera. Here we go. So if I know that this is south, this is north, I can use my first right-hand rule for solenoids. This is single wire. And then you can see that my current flow is this way. So this would be my current flow, like that. This is my induced current flow. So induced current is called an eddy current, And up here, it's the exact same thing, but remember what's happening here. Here, it's going to be attracting. So you have another induced magnetic field. I don't show you this one. You don't have to copy this one down, but it's the same thing, but the current flow is going to be the opposite way up on top. So you've got the opposition, you have attraction here, repulsion here. Both of them act to resist the motion, they oppose the motion of this ride. So how does this ride work? Well, let's look at it. That's the next slide. So that'd be this drop tower. That's the drop tower ride, okay? So this is my first physics class. We used to go to Wonderland every single year. This was my first physics class in 1997. That's how long I've been teaching physics. And that's my class, some of my class students over here on this particular ride. And what happens here is above here, we've got a permanent magnet. We have a south-north up here, and we've got these coils. The coils act like the tube. Same thing. It's like the tubes that we have in what I showed you earlier. But we'll simplify the model, and let's just say that this is the ride. So what's going to happen is you're going to have this. Let me just fix that, like erase this. And now I'm just going to shut the camera off here. Oh, maybe I'll leave it. I'm just going to hold it. Okay, so what I'm going to do is just show you how this works again. All right, get rid of this stuff over here. So what's happening is this. You're going to have your ride. So this ride is going to be up here, and it's going to be falling. So this is your magnet. Well, let me use the same color here. Okay, same color. So this is my ride. There's the magnet. It's falling. Now remember, as it's falling, you're going to be inducing current flow here. So, and it's going to have a pole that's fighting you. So if this is north, if you're going down towards this, you're going to be creating a south pole. So you're going to have this. And then according to my first right-hand rule, I'd have my north. My current would be like this. So this would be my eddy current over here. That's my current flow. And similarly up here, as you're going away here, you're going to have attraction. You're going to have a north-south. And the current flow would be in the opposite way. So you've got these two eddy currents, and what they do is they resist your motion. So this ride is amazing because even if the power goes off, the braking is really just magnetism and Lenz's law and this induction. And what happens is you create a lot of electrical current here as you're falling down. So this ride is grounded very well. And then eventually these things heat up over time as well. These copper strips heat up because they're just the energy eventually ends up as thermal energy. We can also use the same thing on cooktops. Some of you might have these induction cooktops. They work based on induction of current as well. Let me show you a little clip on that. This is some kind of cool stuff. And this is what I'm planning on getting. My next stovetop is going to be an induction stovetop, just because it's so much more efficient.
Consists of a ceramic plate with an electromagnetic coil beneath it. When you turn on the burner, an electric current runs through the coil and generates a fluctuating magnetic field, but no heat in and of itself. However, once you set an iron or stainless steel pan on the burner, the magnetic field induces many smaller electric currents in the pan's metal. Iron is a poor conductor of electricity, so as all these small currents run through the iron, much of the energy is converted to heat. Thus, on an induction cooktop, the heat is coming not from the burner, but from the pan itself. This can make for more efficient cooking.
All right, so we're going to stop there. And again, what's happening here is you've got this changing magnetic field. Remember, the field has to be changing all of the time. So you're changing this magnetic field, and then it's inducing a current here, and the current is inside the pot, and it's the pot that's heating up. I think that's a really, really cool thing. So if you take the pot away, you put your hand on the stovetop, it feels cool. It's such a crazy thing. You know, you don't think about that, but such a neat application of induction. All right. So I want to show you one more here. One more. Great application of induction. Just going to go over here to the side. Any of you guys have wireless charging for your phones? Who's got wireless charging docks or anything like that for their phone? Anyone have that? Or those pads, those charging pads? No one has those? Oh, okay, one person. A few of you, I'm sure a lot of you do, so I'll show you. So here's what I have. And this works in many, many cases. So here's what I have. I'm just going to show you here. So look at the camera for a little bit. Let me just get this out of the way. So down here, this is basically hooked up to my power, right? And what's happening here is this is making, well, it's not active right now, but when I put my phone on here, it starts charging my phone. How does that work? Well, what's happening here is this. This is making a changing magnetic field. So this changing magnetic field here, it goes to a coil in here. So in the back, you have a coil here, and that magnetic field makes this current flow in the opposite direction, right? And what happens is, so keep back and forth, and that is being used to charge the batteries in here. So you can use magnetic induction to charge things. So again, I won't ask you to explain this. This is just showing you real life examples. I even have an electric toothbrush. I don't know if any of you have an electric toothbrush. You put it onto a stand, and the stand charges the electric toothbrush. It works the exact same way. This is all examples of induction. All right. So we're pretty well done with the lesson for now. Just let me see if there's anything else I want to go through with you guys. I think that's it. We're going to stop there. All right. So that's the lesson for today. So I just want to focus on the opposite of what we did before. So this is electromagnetism. We're making magnetism from electricity. Now we can make electricity from magnetism, but the magnetic field has to be changing. And it's always opposing your motion. Whatever you do, it does the opposite. So if I want to come towards this, it's going to resist me. If I'm going away, it's going to resist me. So here, going towards, this is going to be south. It's fighting me. So there's my current flow. If I'm going away, this is going to become a north. You can have attraction, and it's going to have opposite current flow. So you go back and forth, and you make the current go one way. You make it go another way. All right. Just anything else. I'm going to double check to see if there's, I think there's one more application I want to show you. Let me just quickly see if it's there still. Hold on. I think it's on this side. Got too many windows here. I gotta one day figure out how to better manage my windows. No, saw that one. First generator. There's one on microphones. I want to show you how microphones work. Might be this one. Here we go. Oh, and let me show you this one too. I'm going to drag the whole thing over here. So you can see here, this would be the drop tower ride. You can see here how, and look at the ring here. So I'm going to bring this up. Okay. If I'm bringing this up, question for you guys, okay? If I'm bringing this up, what pole do I have here? Is this north or south over here? I'm bringing this magnet towards it. What pole would this be, guys? Remember, we're bringing this up here towards this. All right. So this is moving up, or the ring could be moving towards it. Remember, it's going to fight me. I'm going towards this. This is going to resist my motion. It's going to fight me. So it's going, this should be a north. And if this is north, I want you to use your first right-hand rule. Which way is the current flow going to be in here? Which way is the current flow going to be here? If this is north. All right. So get your thumb at the bottom. Right, here's my thumb. My fingers, which way are they curling? They're curling like this. So should be like this. Let's see what happens. So I'm going to bring this towards. Just switch over here. Here we go. And you see here, there's my current flow. My current flow is clockwise. What if I go the opposite way? If I go the opposite way, the current flow is the opposite. One way, another way. So it depends what I'm doing. So if I'm going towards this is a south pole, or we say north pole. If I'm going towards, if I'm going away, this becomes a south pole. So right now, down here, nothing, north pole, south pole. And if I just leave the magnet, nothing happens. So that's why you need to have a changing magnetic field. Now, the same thing happens inside microphones. I'm going to show you how a microphone works. So a microphone, you're going to have, see this? You have a magnet in here, and there's my coil. And as the coil's moving back and forth, you're making current back and forth. Remember, we talked about this before. So there's my positive and negative. That's where it comes from. So in a microphone, you're using induction as well. And that's how it changes sound waves, compression waves, into an electrical signal that we then play through our various devices after we do that. All right, so I just want that. This is what I want to show, because I know a lot of you guys are into music. So just to understand how music works. So all these are linked online. So bottom line, all you have to do is this. I just want you to have this note done, the top part of this, the top part. Don't worry about the drop zone, the drop tower. I won't ask you this. I won't ask you that. But you should be able to know this up here and this generator. It's they're really the same thing. They're exactly the same. So you're going to have a diagram on your, or two on your test on Thursday related to this, okay? So just so you know. So that's all you have to know. Now online on the website, there's all this stuff over here. Just ignore that. I'm going to put down optional. This is if you want to know how loudspeakers work or these different devices and you've got a little bit of time, even later in the week, you know, if you have a bit of spare time, I'll leave the link up. You can check that out. All right. So all you have to do today, just work on, as I said, I'll be specific here. Just work on the diagrams related to Lenz's law, and I'm happy. Apart from that, what you can start working on now tonight is maybe looking at some of the review questions. These are some of the review questions for the problem solving we're going to have on Wednesday.